Yeah, before I start, this will be a talk which talks about our journey. In no way do I claim that we are leading the digital transformation charge in pharmaceuticals, but I think it's always helpful to show different stories of things that people are doing. So hope you enjoy it. So where do we sit as CatSci? Well, we're starting probably to see some fruit. Is there a pointer? Was the It's fine. Starting to see some fruit in how we're using different tools. So distinctly on the 2-3 type boundaries, and I'm sure many people are in this space. So the real reason that people come to these talks is to hear about the company that are presenting. So I'm going to share a couple of slides. So CatSci are a pharmaceutical CRO, an innovation partner. We focus most of our work in process chemistry, but we've branched out into all of these areas over the last 3 years. I'm particularly excited by our move into oligonucleotides, which we launched in April this year. We're growing that business really well. I'm very excited that probably in a week or so we will launch our GMP analytical science business, and that's been a long journey of regulatory approvals and setting up our policy systems for that part of the business. So really excited to be part of that journey. So CatSci are UK based. We have 2 sites in Cardiff, our HQ and our laboratories, and then our analytical facility is set up in London. We won the Queen's Award last year for exports, so really proud to see that as well. Great. So story so far. Why connection to Signals and PerkinElmer? So about this time last year, we finished our paper evaluation about changing our ELN system. We wanted to embed a new system with 70 users, focused mostly around process chemistry, analytical science, and material science. On that journey, we decided we'd launch an oligos business, so that became part of the description as well. Then in Q4 last year, we started that practical evaluation, made the decision about which tool we were going to go for. Obviously, we chose Signals, and then we launched that with five key templates in Q1 this year. So we launched in March with deployment and training, trainer, and then we let loose the chemists on all the templates, which perhaps was, that they were very creative. And the template explosion in Q2 this year, which we ray back. And then since then, we've been working on different productivity tools and connecting all of our systems together. And really, the theme of digital transformation at CatSci this year has been making sure we've got systems which can talk to each other properly, and then connecting them up. And Signals is part of that journey. This is the team who did the deployment. Really passionate team who worked really hard to deploy so quickly. They did this in 2 months. And it was a great job. So thank you to everyone, particularly to Guy at the end, who has lots of experience in this space. So you'll have seen many pictures like this. We're trying to connect up all of these types of systems, as many people are. One of the privileges of being in a small company is I get oversight of all of these systems, and so there's at least one point of contact for understanding how they're going to connect together. So I'll focus mostly on the ELN actions. And this year we've managed to connect all of these things, all of these things together, and I'll talk about some of these as we go through. We made a decision at the beginning of the year to set up a small development company called LabLinks, and this is the group which are doing all of our sort of API building and our digital work. So if anyone's interested and wants to have someone to help out in building tools which might connect with your systems, let us know. We'd love to work together. Okay, so some examples. When we started working with Signals, I was disappointed, I'm honest, to see that there wasn't a native sort of management dashboard. Maybe there is something now, but we set about using the API suite to pull out data, put that into a database, and then this dashboard then updates live over the top. Having this kind of functionality is really important for managing the labs. So having your quick API integrations, pulling that data out, you can connect this into Power BI or whatever BI tool you're using, into Spotify if you're using Lumi. So a very simple tool, really, really powerful. We don't have access to some of the tools that Alistair was talking about before, so we've put in place a simple Python scripted data visualization tool, which lives as an external action inside of Signals. So what happens is you click on your external action, a little logo, and then the data will ask you which table you want to extract information from, or you can upload an Excel file or a CSV file. It will process that data, aggregate the data, and then display a sort of user interface which allows the user to choose which from I think we've got four different visualization tools at the moment, and allows you to customize those. So behind that, there's a load of work which says, okay, which columns are able to fit into which are they categorical, are they continuous variables, all of that kind of stuff. But it really saves the chemists some time. Even building, you'd be amazed at the diversity, well, you wouldn't, I'm sure, but the diversity of presentation of data that you can get from a group of 70 chemists. And so what we wanted to do is try and standardize around that and speed that process up for people so that they weren't producing all sorts of different plots for through Excel, which would take a bit of time. They can still do that if they need to do something different. And then we keep building the number of visualizations that sit behind this very quickly. And then the final quick example I'll give before I move on to thinking about computer vision. So we use the Mestre platform for our analytical work. And so we've built a workflow that comes from Signals. This is the old Signals logo I just noticed. From Signals, you create your experiment. This API connected through. You run your analysis. All the data is pulled out, and then that gets pushed into the NGears tool, which is an automation tool and data processing tool that the Mestre platform have to automate some of the data processing. So it converts that file into a standard Nova file from all of the different vendors of our analytical equipment that we have. Does peak picking and outputs that sort of information, and then pushes that data back into Signals Notebook as a file, and then as tables if people need that. And this is something we developed with our previous ELN, and we wanted to mirror that again. And it was great to work with the Signals team to make sure all of the APIs connected through to do that. So this section was a sort of story about what can you do with the API endpoints, loads, and there'll be infinite ideas that people have. And that was one of the reasons that we chose Signals Notebook, because we knew that facility was so powerful. So I'll switch gears now to talk a little bit about the computer vision collaboration we have with Reach Industries, and they have a product called Lumi, and we're helping them to develop the this platform. So if you want lots of information about that, well, chat to me later, but reach out to Silas or to Chris, and they'll be able to share lots of information about the processing behind and the AI tools that they're using to process this data. So what is Lumi? It's a camera. It's a static camera that you set up in your laboratory. It can watch reactions, people processes, dials, whatever you want to look at, and then it will take that data, push it into their cloud app, and then start to extract information from that. So it will start to take process information if you're looking at a reaction, for example. So it will notice changes with time. So it could be color, turbidity, volume, phase change, phase split, liquid transfer, whatever you're looking. If you can see it, then it can turn that visual change into some sort of process parameter and then plot that with time. It could be a dial or something. I had it looking at pressure on our nitrogen system, which had some issues for a while, just to watch when things went down. And then I could turn this normal dial that was on the normal pressure gauge into a sort of digital pressure gauge just by pointing the camera at it. So there's hundreds of applications like that. We heard yesterday and through this conference bits about digital twins. So what that can look like for us in process chemistry is around scale up. So in process chemistry, we're designing a new route to manufacture. So we know what the target molecule is, but we need to design a manufacturing route to that. And part of that journey, once you fix the chemistry, is managing the scale up from trial reactions, which might be at a few mils or in plates, all the way through to what could be ton scale. You need to model the changes through that. So what you can do is you can map your vessels. So that includes the geometry, the mixing behavior, heat transfer parameters, all of that sort of thing, and turn that into essentially a digital twin of your reaction vessel. We would then monitor performance of our digital twins through single point analysis. So you take HPLC at certain time points, and then you plot how well the model is doing based on that. But that's obviously single time point data. Traditional methods to do this in real time involve process analytical technology, and that's something that we do as well. But these tools and probes tend to be very expensive, and you can't, or we don't have the capability to map every single reaction that we are doing. And so we were looking for tools which be a proxy for this, and then monitor things in real time based on visuals. And that's why we're collaborating with the Reach team. So a bunch of videos. So here's a pretty reaction. So you'll see some changes. So this is a Minsonobu reaction, which has got lots of color changes over time and makes a good case study. Lots of our reactions change from pale yellow to slightly darker yellow, or not turbid to slightly turbid. So you can pick up all of those changes with Lumi, but they don't make such nice slides. So we have this example. So you can see it changes from a pale yellow to a rich red color. In this example, that someone's bumped the camera a few times, but you can see the kind of information that you take. And even just showing this as a video gives a great picture to a customer around what is happening in the reactions that we're running. So that's rich data as it stands. But really, what we're looking to do is to pull out some more of that information. Just to note, this will cycle through. Notice that very quick color change. So it goes from pale to yellow really quickly, and you'll see that in the plot in a minute. So this is what the data starts to look like. So you can pull out lots of different color space information from that data. So here I've plotted the red, green, so RGB data and the LAG, so I remember, different kinds of color space, and you can pull those out. And you can see here the reaction progress. So you've got a plot here. Nothing's happening. It's a straight line for a bit. Let's look at the normalized data. So this is your induction time. Then you've got a traditional reaction profile. So increase and then leveling off as the reaction's completed. So even without any modeling, you can say, when you put to this space, it looks like your reaction is finishing, or it's stopped for some reason. So even without any of that modeling information, you can get some useful data about it. When you put on the other color spaces, you can see that very fast color change that you notice. So when that thing swapped to yellow, you can see that very distinctly. So even from that information, you've got a very nice now plot of that reaction progress. And what we're able to do is start to use that information as we scale up from small reactions to large reactions to demonstrate to customers that we have control of our reactors. We understand what's happening in the chemistry, we understand what's happening in the vessel itself, and then we can start to model that. So here you can see, just with pictures, the sort of different stages of that reaction. So what does that look like then? We've had that 1 liter, we scale that up to 5 liter vessel. It's a different manufacturer's vessel. So the geometries are different, the stirring head was different, but we're able to model all of that and then match that together to make sure that we have control of our chemistry. So here you can see in the pale line, you can see the data from the 1 liter vessel, and then in the dark lines, you can see what happened in the 5 liter. So there's some noise here, and I'll talk about that in a minute. But you can see on the red lines that the reaction progress really follows very well. And that shows that our modeling, our digital twin was doing its job, the modeling worked well, and we're able to have control of this reaction as we scale between different vessels. And then pictures from the 1 liter at the top and the 5 liter at the bottom at the same time points. So this is not complete technology. One of the disadvantages of using cameras is, particularly on glass vessels, is that there are reflections, and you can see that in the data. So the one thing we're working on at the moment is be able to filter those out. So they're obvious when you look at them by eye, and so if you can see it and make a decision as a human, you will be able to code an algorithm to modify that. But when you change conditions in the fume hoods, even when you normalize the color data, you still have some changes. And so if you were trying to get very, very precise model data out of this, there would be some challenges. But in terms of understanding reaction profiles, understanding the overall kinetics rather than the specifics, you can get some great information. But there's further work to go, as with all these things. And I liked this example. So this wasn't an intended component of this reaction, but you can see here, you get this, the stirrer has failed overnight. So the story here was that someone took their end of day sample at just before 6 when they went home for the day. So we had data which showed the reaction was stable then. They came back in, this was a whole point, came back in the next day and took another sample, and the chemistry is okay, and that's great. But now, instead of being able to just say that at some point overnight the stirrer failed, we now have data which we can share back, which is useful to say, okay, this reaction is stable for a hold point for this much time because we have this data changed, because we have the image that changed at this time point, and then from when the chemist came back in the next day. So really useful information. So if we monitor all of our reactions like this, we'll have access to that kind of information. And this is much cheaper to run, much more universal, much easier to set up than training a chemist to use React IR from Toledo or Blaze tools or all sorts of different things. This is now integrated into the Lumi platform. Is now integrated into our ELN platform into signals. This is definitely an alpha version, so it's a little bit patched together so I could have something to present. So the Reach team have built their API connections over the past couple of months, something we've proved them last week. So this is a very early version which goes through a quick web page to integrate these two API endpoints. But now what we're able to do is, click on another external action, which opens the data in the Reach, the Lumi platform. Then you can connect your two experiments together in those two different platforms, and then push data between the Lumi platform back into Signals Notebook. Chemists find it very difficult to move between tools and platforms, and so we really want to have Signals as the hub through which they can access all of these different tools. But Revity aren't going to be designing all of the best components, and so we need to have a really strong API endpoint to be able to connect different things together, and that's what we've seen. So, in conclusion, connecting things together, it's a bit like synapses in the brain. The more connections you can have between systems, gets more complex, but you get lots more information. We can start to visualize that data in lots of different ways. Collaborating with different groups, so thanks to Revity and to Reach and to LabLinks in this case for all of their collaboration. And keep going. So this was bits of story of things that we've been doing over the year. I'm sure that, I've heard this week amazing things that people are doing already. So I think it's a really exciting time to be involved in science and the digital transformation aspects of that. So thank you. And any questions?